Hi, my name is Kianna Hendricks, and I'm a student at North Carolina A&T State University. And my project is entitled A Stacking Ensemble Approach, where I leverage plasma proteomics, metabolomics, and clinical data for COVID-19 severity prediction. So let me start with what are proteomics and metabolomics. And proteomics is essentially the study of a large collection of proteins, and proteins are really the workhorses inside of our cells. And this field studies what they do and how they interact with our body. And then metabolomics is the study of a large amount of metabolites, and they are small molecules that are the result of or necessary for our cellular processes. So together, they can give us an overview of how our bodies respond to diseases like COVID-19. And that is why they are important for any sort of model that makes predictions about severity. And then a stacking ensemble is a machine learning algorithm that produces predictions by strategically combining the outputs of multiple base models. And they really give a more accurate forecast if you have information from different data types and combine them together for more diversity. And next, the question I asked is, can a stacking ensemble machine learning model that integrates plasma proteomics, metabolomics, and clinical data accurately predict COVID-19 severity? And the objective really was to develop a model that can accurately predict COVID-19 severity using multiple types of data combined together. And so the method was the stacking ensemble method. And the results were enhanced predictive performance compared to the base machine learning models themselves. And it offers a comprehensive insight into COVID-19 severity from different perspectives. So we all know that the COVID-19 pandemic has had a huge impact on our world. And one of the biggest challenges when it comes to COVID-19 management has been the prediction of disease severity, which is important for being able to allocate resources appropriately for different patients. And multi-omic data can offer a comprehensive overview of an individual's health status, and being able to garner information from those different data types can give us a better understanding of disease severity. So my project built upon Demasaki et al.'s work, which included proteomics and clinical data into a traditional machine learning model. However, if you have integrated into a ML model, multi-omic data, comprehensive model evaluation metrics, and also ensemble metrics. And that is what this project aimed to do. So for the dataset overview, I used a deep multi-omic longitudinal study, which contained data from 209 COVID-19 patients. And this study was originally created to identify risk factors for long COVID. And so here is an overview of my methodology, starting with the 3 different data types and then going through pre-processing. The proteomics and metabolomics went through the same pre-processing steps, and then model tuning and selecting the best performing models to include into the final stacking ensemble. And then here's a closer look at the process for a stacking ensemble. So the data pre-processing. So for this project, I extracted just time point 1, which is the initial diagnosis. The original study had 3 time points, but I felt that the initial diagnosis would be the most important when it comes to applying such a model in the real world. And then, of course, I had reduced the data set to filter out any patients that didn't have omic data. And then for feature selection for the clinical features, I use recursive feature elimination. And for the omic data, I use principal component analysis and applied it to the proteomics and metabolomics data. Basically for dimensionality reduction, there were a lot of proteins and a lot of metabolites. So basically a lot of columns, but very few rows. And in order to have the data in a more suitable format for a machine learning model, I had to go through that process as well. And as you can see, the final dimensions after compared to the initial dimensions. And then for the final clinical features, there were a lot of features, but based on just domain knowledge and also the most informative features from feature selection, these were the final features for the clinical data. And then another important part was severity, class, and balance. As you can see, there is a lot less of the severe cases within the data set, and that is important to consider when it comes to how effective and informative a machine learning model can be. So that was another thing that I had to be aware of. And then when it came to model search and tuning, so I started with 10 classifiers or models. And within the training and the selection of the models, I also incorporated techniques to address the severity class imbalance that I previously mentioned. So I use a combination of border smote and random undersampling together to address that. And then for the stacking ensemble, so after selecting the initial 3 models for the 3 data types, they were input as features into a stacking ensemble. And in order to have a stacking ensemble, you also have to have a final estimator. So I chose a logistic regression, and essentially I chose these base models and the final estimator to have a diverse amount of models, making sure none of the models were really similar in architecture as well. And then I also evaluated them across the metrics you see here. And here you can see the performance metrics overall. And you can see that generally the Stacking Ensemble outperform the other models. For the clinical model, it's important to consider that the simplicity of the clinical data compared to more complex data like biological data, which is why it generally performed very well in general. But we wanted to ensure that we included information about all different data types together to have a more informative model. And also, one thing that was really important was recall severe, which is really the recall of specifically the severe cases of COVID-19. And of course, we know that that is basically the most important case of COVID to consider, and making sure that we accurately are able to predict that. And here you can see the confusion matrix. So 0 is for mild, 1 is for moderate, and 2 is for severe. And as you can see, there were no false predictions for the severe. However, there were a few for mild and moderate, but comparatively, the model performed well overall for the accurate predictions on the diagonal. And so for the discussion, excuse me. I found that integrating multi-omic and clinical data into a stack ensemble does have promising utility for COVID-19 prediction. You can see that incorporating numerous diverse models with diverse types of data had a relatively overall high performance, especially where it mattered within recall severe. And of course, the emphasis on the recall severe helped minimize the false negatives. And I would say the limitations would be that the sample size was relatively small. And also, like I said, the class imbalance, while I attempted to address it, is still inherent to the data overall. And for further research, you could benefit from larger data sets. And also another important thing would be to incorporate external validation data sets as well, to validate it with different types of data from other studies as well. And then also it would be important to consider the biological implications, looking into the models and what they consider the most important proteins, most important metabolites for severity prediction, and be able to validate that against pre-existing biological research and studies would be important as well. And thank you.